the current manufacturing, the data is fragmented and stored in different data silos. These data silos also have another problem, that sometimes the data is duplicated and it creates inconsistency in the data and also incompatible information that we have about different products and also the systems and informations. Most of the times this information is stored in duplicated systems that results in lack of information and data consistency. This creates another problem, which is the lack of overall understanding of the systems and data in the system, and it creates a poor decision-making process. In Industry 4.0, when everything is agile, there is a need for coming to data and also providing the most recent information about the assets that we have in the system. So this data that we are talking about, that from different data silos, should be somehow consistent and available for a whole broader look at into the system. There are different definitions of digital thread in the scientific field, but all of them are focusing on linking data sources together to provide a whole understanding of the whole product cycle. In T4T, we are mainly focused on logistics, assembly and quality assurance, and not the whole production life cycle. We also consider the output of the digital thread to be provided for supporting decision making. So with this introduction and definition, we also consider two assumptions for the project. One is that the digital thread is not going to control anything, but it's just going to support decision-making process. And the other point is that for us in the concept of the project and also digital thread, digital twin is a single source of the entry. Of course, we will explain about it later. I am Nastaran Moarefvand. I've done my master in RPT Kaiserslautern in computer science, and I've been working in DFGAIA as a researcher for the last 3 years. My background is semantic web technologies, ontologies, and knowledge graphs. And in the T4T project, I'm mainly focused on the topic of digital thread. To find a suitable solution for digital thread in the context of T4T project, we defined some user stories so we can provide specific answers for them and create a bigger concept out of these user stories. So the first user story is about the arrival time of a part for assembly. So the worker can decide if the part is there on time and they can carry their job, or they need to postpone the next step or wait for the material to be arrived. The next user story is determination and localization of the damaged workpiece carrier. So the problem here was that sometimes it happens that a transporter damaging the parts that it's transporting. And once it's noticed, then there is a need to localize this transporter and also stop that from damaging other materials. This was our second user story. In the third user story, we have the feedback loop to the assembly worker. So there is sometimes the need that the worker needs to know what has been done in the last, for example, week, and what was the failures, for example, on a specific assembly job, so they can improve it, or they can do some reworks and fix the errors. These are the user stories that we define for the digital thread. How we proceed with the solution is that for us, digital twin has an important part in the system, and also we define a knowledge base. So the whole architecture of the digital thread consists of these two important parts. For the digital twin, we choose AES or Asset Administration Shell as a digital representation of the assets in the factory or in our ecosystem. These digital twin repositories are connected to different data sources and also services. Apart from this digital twin repository, we also have a knowledge base. This knowledge base is the core part of the system that does the logic behind the scene. So as you can see here, different ontologies can be used in this knowledge base, but the most important one is the one that we called it here DCAT version 3. As you can see, This solution is based on different standards. First is based on the asset administration shell, which is provided or also promoted by Industry 4.0. And also we have the knowledge base and this DCAT ontology that is also based on what's happening in the web and how the data is stored and also findable on the web. If we want to go more deep to the AES repository, as I already mentioned, is based on asset administration shell. And the way that a graph is generated out of these AESs and also this repository is created is based on the asset administration shell meta model. So it's also in line with the standards that's already been provided. The other part of the knowledge base that we have apart from the AESs are these DCAT ontology. DCAT ontology is a resource description framework. Vocabulary that is designed for finding and also identifying and linking the data on the web. It means that the data that there is already on the web, it's either a data set, data series, or services. They are used and defined by these DCAT3 ontology in a way that everyone can access them or find them. There are also different ontologies that can be used in the knowledge base. For example, we can talk about production environment ontology, which is focused on the different on the environments that we have on the factory. For example, different sites, different floors, different assembly or different stations that we have. So based on these additional knowledge that we provide to the system, we can also provide more context-aware information for the user to make the decision. Here in this slide, we can see that there are different data sources and services available that with the help of them, the information and the real-time data is written to the AES and a digital representation of the asset or digital twin is created. These data sources then are hosted by BASIX. And after that, as I already mentioned, a graph is generated from these AESs, and with the help of the queries, there is also a way for answering to the questions that the users have and support what they want to do and provide help for decision making. So for creating AESs and defining the digital twin representation of the assets in the system based on the user stories, we define different AESs. So as you can see in the slide, the one is related to the truck frame. This one was more customized, but the other one, for example, semi-trailer truck and also workpiece carrier, we used submodels there that they completely came from IDETA. So we also try to be in line again with the standards provided. For the truck frame, one of the submodels that it was useful and also it was customized for these specific user stories that we have was the quality assurance submodel. In this slide, you can see the overall view of the pipeline of the data that it was used in the digital thread. As I already mentioned, we have different AESs that they are hosted in BASIX. The one good point about BASIX is that it also provides the AES registry. So it gives us an overview about all the AESs that we have in the system. After that, the graph is generated based on these AES. As I already mentioned, it's based on the AES meta model, and it's always synchronized with the data that we have in the AES in 3 different layers. First is the AES itself. Once AES is added or removed from the system, we also have that in the graph. The other one is a submodel is added or removed from the AES. We also have the synchronized graph representation of that, and also the values inside the AES, which is the most important part because it's a digital twin representation. We can also have them updated and synchronized in the graph. After that, based on the queries that we have and also the graphical user interface, then we can see or we can provide different answers to the questions for the users. And finally, these questions and their answers are shown in a chatbot into the graphical user interface. Our proposed solution, as I already mentioned, consists of two important parts. One is the AES repository and the other is a knowledge graph or ontology that we will talk about that in more detail. We hosted all of those information in one graph database, which is a label property graph. As you can see, these nodes up here are showing the AESs and different assets that we have. Here we can see one example of the AESs. It shows the semi-trailer truck AES, and the nodes in the green you can see they are the submodels that exist in the AES. Other nodes are also generated based on the data that we have into the AES. This part of the graph shows a representation of the ontology that we have. Here we can see that there are different dataset series, and also services defined in this ontology. The whole data that also exists in the digital factory layer is the same as this data that already are available on the web. But we create an application profile based on this DCAT ontology. It means that based on the user stories and the systems and also the services and data sources that we have into the system, we created different instantiation of these and added them to the graph. As you can see, there are different data properties that can also be added to these data sets or services that we have. For example, we can see what's the title of a data service or a data set, what's the URL link to access that, what's its status, if it's active or it's not active or it's not available anymore. And for example, if it's a tool or technology, what's the version of that? Of course, DCAT ontology is bigger than the examples that you see here. They are created only for the user stories that we have into Infotrucks project. Here we can see an example of a MongoDB in the localization system in order to keep track of the live data of the workpiece carrier or different transporters. So here we can see that we modeled this database in the ontology, and we can also provide some more information about that. For example, what's the version of this MongoDB, how to access it, what's the endpoint URL for that, if there is a description for this URL, how to access that, and other information that help linking the information and different data sources together. With the help of the queries, we can provide different information for the support for the decision making. As you can see, there is a list of them that it was useful for our user stories. For example, in this one, we can see the status of the available workpiece carriers in the system, if they are okay or if they are damaged. For one of the user stories, we needed to provide a feedback loop to the worker in the assembly station. For this means we had this notification bar in our GUI or graphical user interface, so the user can see in the last week how many errors or the orders with errors there was in the system, and also in each of them how many errors exist. By clicking on each of the orders, then the user can also see a picture of the error that is captured by cameras, and also the position of the error exactly on the frame. Here you can see the chatbot that we also have that in our user interface. Here you can see one of the queries that I already showed in the graph. But by clicking on the detail button, then we can see more information about the workpiece carrier. For example, its current location in the shop floor, or more information such as the parts that the workpiece carrier is capable of transporting, and also its current location on the system, its name in the system, and information such as this. We also can provide the same information about the product. The key benefit of digital thread is that it provides a whole overview over the data that exist in the system, and it can also support the decision making. It can help transform data to a strategic asset and also make the organizations and factories more agile to the changes in this modern industry. This solution can provide two benefits. One is that it's scalable. It means that it doesn't matter how big the domain is, and also it's that it's transferable. So in different domains, it can also be applied and used.